Hey everyone, this is Fran. I'm re-recording the lecture that I gave yesterday in person because there were some audio and video issues due to my limited bandwidth for Wi-Fi here in Portugal where I'm spending the holidays. So hopefully with this recording, you guys will better be able to understand what I'm saying and writing and be able to complete your final homework assessment of this first semester in 2020. And with that, I guess let's get started with lecture. So today I will be concluding our series of discussions on mathematics for quantum. It's the third lecture that we're having on this. And we're going to be going through a lot of really, really cool topics. So again, before I get started, make sure you're not distributing these materials outside of the course, outside of the class. And so yeah, let's take a look at today's syllabus. We have the lecture divided into two main sections. In the first part, we'll be doing our mathematics for quantum. In the second part of the class, we'll be giving a preview of semester number 2, basically getting you guys hyped about all of the really cool quantum content we'll be covering in 2021 over the next few months. So hopefully you guys will stay on. The class will really start to pick up. We'll do quantum mechanics, quantum information, quantum algorithms, experimental quantum information processing, quantum applications and research, and more. It's going to be a really great time. But before we get there, we're going to need to conclude our mathematics for quantum, really building up those foundations to make sure we can understand all of the quantum to come. And so before we get started, I just wanted to take a few moments to note that the first part of today's lecture on vector spaces might seem a bit abstract. And I guess we're giving you guys this lecture more to make you familiar with sort of linear algebra terms that you'll oftentimes hear and maybe see if you read further into the quantum computing literature. If you take a linear algebra course, you'll spend a significant amount of time really formalizing your understanding of this. For the purposes of this class, you don't need to have a really formal understanding of vector spaces or be able to prove whether or not things are vector spaces and so forth. But there are a few important concepts that we'll want to take away, and I'll try and make sure I emphasize those. But if you feel a bit overwhelmed, don't worry, because this definitely is the most abstract bit of today's lecture. The second part of the lecture on eigenvectors and eigenvalues. The second part of the lecture today on eigenvectors and eigenvalues is one of the most important concepts, arguably, in linear algebra for science and engineering. If you go on to take further STEM classes in university, you'll see these pop up all the time. And we're really going to try and emphasize to you guys sort of the geometric interpretation and make sure you have a understanding conceptually of what eigenvectors and eigenvalues are. We're going to also walk through calculations and teach you how to calculate them, but that's not as important since you can go and do that on any online calculator. So with that note in mind, just my final point I want to emphasize. In this class, we're teaching you a lot of linear algebra, but we're not doing it very formally. So make sure when you get to university, you do take a proper linear algebra course, because as we've been saying, and even as Jay Gambetta said in the opening of our first lecture, linear algebra really is key to quantum mechanics, quantum computation, quantum information. So making sure you get a good grasp of that is really important. But by taking this class, you're already a step ahead of the game and really well prepared to take those university courses. So with that, let's dive into today's lecture, starting off with our discussion on vector spaces. And in order to introduce the concept of a vector space, I wanted to present the formal definition. And actually, this definition should be fairly intuitive. So a vector space is a collection of vectors which can be added and multiplied according to the properties listed in blue. Now, I know there seem to be a lot of properties here, or axioms, but these axioms are actually all pretty intuitive and things we already expect, for example, when we do scalar addition and multiplication, so none should seem particularly surprising. I'll quickly run through and explain in words what each of these axioms are to give you guys a taste. And so this is sort of the formal definition of a vector space. But again, for the purposes of this class, you won't need to be proving that something is or is not a vector space. But it's just a good idea to note that if you have vectors which lie in a vector space, all of these properties are true. So let's start off with the first axiom, which basically tells us that if we have two vectors in our vector space and we add them, order doesn't matter. And this, of course, generalizes to having addition of even more vectors. The second axiom tells us that if we are performing an addition of multiple vectors, it doesn't matter, for example, whether we add the second two vectors first or the first two vectors first, the result will always be the same. This third axiom here tells us that a vector space must have a unique zero vector, such that when we take any vector in the vector space and add it to the zero vector, we get back the original vector. This fourth axiom here tells us that for every x, or every vector in our vector space, there is a unique negative or inverse vector, such that when we add our original vector to its inverse, we get back the zero vector. Now moving on to multiplication, if we have a vector in our vector space, there should exist a scalar 1 such that when we multiply it by a vector in the space, we get back the original vector. The sixth axiom tells us that if we are taking scalars and multiplying them by our vector, it doesn't matter if we do the scalar multiplication first or we multiply one of the scalars by the vector first, the result will always be the same. This seventh axiom, there's actually a typo, it should say AY. And basically this tells us that it's distributive property. If we have a scalar multiplied by the sum of two vectors, that's equivalent to multiplying the scalars by the vector and then performing the addition. And the same goes the other way around. If we have scalars that we're adding and then multiplying by a vector, we could do the scalar vector multiplication first and then add the resultant vectors, and it all gives us the same result. So those are the principal axioms for a vector space. And again, they're all pretty intuitive, things that we would expect and hope we could do with vectors and scalars. So if you ever hear that your vector lies in a vector space, you should note that all of these properties hold true for that vector and the remaining vectors in the vector space. And then I just wanted to conclude this definition of vector spaces by giving some examples. We'll start off with the set of two-dimensional real vectors, which again, notationally, I've used this notation a few times in the class before, but let's remind ourselves. So this fancy R basically just tells us that we're working with real numbers. And having this 2 superscript here basically tells us that our vectors have two components. So to give some examples, maybe we'd have 1, 0, 7, -8, 2, 3, and so forth. So all of the possible vectors that have two components and only real components comprise R2. Now, similarly, we could define C2, where in this case, the fancy C tells us that we are no longer constrained to just real numbers, but can instead have vector components with any complex numbers. And so some examples of this would be for example, I0, 1 e to the I 3 pi over 4, maybe 2 plus I, 3 minus I. All of these are vectors which lie in C2. And we could go and define higher dimensional vectors, for example, R4. That's the set of vectors 1, 0, 1, 0, 3, 3, 4, 1, and so forth. So again, this is the set of vectors with 4 components, all of which are real. So hopefully that makes sense, and generally we'll tell you what vector spaces we're working in. So now let's move on to the notion of linear independence, which is an idea that we've actually been hinting at throughout all of our discussions in linear algebra. It's kind of a generalization of the idea of orthogonality. So let's take a look at it. So given a set of vectors, v1 through vk, we look at all of their possible linear combinations. And we're going to remember now what a linear combination is. A few lectures ago, I gave the example of a fruit salad being a linear combination of apples, bananas, and blueberries, and so forth. What makes it a linear combination is, in the case of vectors, you have base vectors that you're adding together, and they're scaled by these scalar coefficients. So to determine whether or not a set of vectors are linearly independent, we have to consider all possible linear combinations of those vectors. And if it turns out that the only way to get the 0 vector as a result from our linear combinations is by setting all of the coefficients equal to 0, a trivial solution, then we say that the vectors are linearly independent. And so why is that? Well, if I want to make the 0 vector, right, if I multiply if all of these scalars are set to 0, then of course it's trivial that we'll end up with the 0 vector, right? Because all of the components in those vectors will turn to 0, adding 0 however many times still gives us 0. If there was a set of coefficients for which any of our c's was non-zero, but we could still get to the 0 vector, then that would mean that all of our vectors were instead linearly dependent. And I know this sounds a bit abstract, so let's go through and give a few examples of what linearly dependent and independent vectors are. So for linearly independent, we can start off with the simple example of 0, 1, 1, 0. So the two vectors in this set are linearly independent, and why is that? Well, if I tried creating a linear combination of these two vectors and set it equal to the 0 vector, if I, for example, said that A had to be non-zero, then I would get vector if I said A and B both had to be non-zero, I would get the vector BA, and there's no possible way that BA could be equal to 0, 0 unless both A and B are equal to 0. So these vectors are linearly independent, and more intuitively, what does linear independence tell us? Well, there's no possible way that looking at using just a linear combination, for example, the first vector, I could get the second vector, and vice versa. So let's give another example here. This could be example 1. In this case, we have the further property, right, that each of these vectors are orthogonal to each other. And why is that? Let's do our quick check. If we took the inner product of the vectors 0, 1 times 1, 0, we would get 0 plus 0, which is equal to 0, and thus orthogonal. And as it turns out, in any circumstance, orthogonal vectors are actually linearly independent. However, the reverse direction doesn't hold. So linear independence does not necessarily mean that the vectors are orthogonal to each other, and we'll give a example of that now. So if we have the set of vectors 1, 0, 2, 1, these vectors are actually still linearly independent even though they're not orthogonal. Why are they not orthogonal? If we take 1, 0, we multiply by 2, 1, we'll get 2 plus 0 equal to 2. And since 2, of course, is not equal to 0, our vectors are not orthogonal. That being said, the vectors are, in fact, still linearly independent, right? Because if we try to create the 0 vector using these two vectors, we would have a times 1, 0 plus b times 2, 1 equal to 0, 0. We could, for example, go and subtract a from one side or our first vector and move it to the other side. So we would have b 2, 1 equal to negative a 1, 0. But in looking here, right, there's no possible coefficient, or there's no possible scalar that we could set a equal to such that a times 0 is equal to b times 1, right? Unless b was equal to 0, in which case, if b then was equal to 0, we would have 0, 0 equal to negative a times 1, 0. And in order then for this 1 to be equal to this 0, well then a would also have to be equal to 0. So the only way that this equation here is satisfied is if both a is equal to 0 and b is equal to 0, which means that our vectors must be linearly independent. Now, to give some examples of linear dependence, let me just write down an example. So our first example will be the set of vectors 1, 0 and 2, 0, where we can tell that these vectors are linearly dependent. Let's try writing out our linear combination of them again. 2, 0 equal to 0, 0. So is there a possible non-zero value for a and b such that a plus 2b equals to 0? And in fact, there is, right? We can solve for this. A equals negative 2b. So we could, for example, if we set b to be equal to 1, a equal to negative 2, then we have a solution. So we have a set of non-zero coefficients for which we can create a linear combination of the vectors to get the 0 vector out. And so I think that is a good example of linear dependence. Let's go through another one. So in this case, let's move to 3 dimensions, get a little bit more fancy. 0, 1, 1, and 2, 4, 2. So just in looking at this, right, we see that 2, 4, 2 is in fact a linear combination of the other vectors in the set. So this can be expressed as 2, 1, 0 plus 2, 0, 1, 1, right, which is equal to 2, 2, 0, 0, 2, 2. And we see, of course, that this is equivalent to this. So since this third vector can be expressed as a linear combination of the first two, and alternatively, we could have said that this vector can be expressed as a linear combination of these two, and so forth, all the possible combinations, these vectors are linearly dependent. And I guess the names themselves, right, give us some sort of intuition. If the vectors are linearly independent, there's no possible combination of vectors in the set from which we could create another vector in the set. All the vectors are independent of each other. Whereas if they are dependent, there is a way of combining a subset of the vectors in our set to create one of the others. So one of our vectors is dependent upon the other vectors in the set. That's why we have these names, linearly independent versus linearly dependent. And if you wanted to potentially relate it back to our example of fruit salad, well, we know that, for example, our fruit salad is a linear combination of the fruits. So if we had the set, for example, fruit salad, apple, banana, strawberry, and so forth, this set is linearly independent, right? Because we can create a linear combination of apple, banana, and strawberry to get our fruit salad. And furthermore, our fruit salad contains apples, bananas, and strawberries. So this set would be linearly dependent. But if instead we just had the set apple, banana, and strawberry without the fruit salad, all of these fruits are independent of each other. They have nothing in common, so we could say that they're linearly independent. This is just an example, not mathematically rigorous at all, but just hoping to build a bit of the intuition. So hopefully this makes some sense, and we'll see this concept again when we conclude this section with our discussion of bases. But before we get to bases, we need to do a bit of practice and then talk about the idea of span. So I'll give you guys a couple minutes right now to try and work on this problem before I start going through solutions myself. Actually, since you guys are watching a video, I realize you can pause the video, so maybe I'll just go through and start working through the solutions myself. If you need some more time, make sure to pause and try it yourself. So here, I basically asked you to state whether the following vectors are linearly dependent or linearly independent. And let's take a look at this first example. So we have -3, -6, and 1, 2. Now, if I was to take -3 times 1, 2, I would get -3, -6, right? So we can see that -3, -6 is a linear combination. In this case, it's not really much of a combination since there's only one other vector, but this second vector is dependent on the first, and similarly, I could have also said that 1, 2 is equal to -1/3, -3, -6, meaning 1, 2 is dependent upon the vector -3, -6. So these vectors are clearly not independent or linearly independent. So we'll write linearly dependent independent. All right, so now moving to the second example. In this case, we see that we have three-dimensional vectors, in which case it's very similar to the previous example we gave, right, where we saw in 2 dimensions that these vectors were linearly independent, right, because they're orthogonal. In this case here, because our non-zero components are all at different locations, if we were to take an inner product between them, for example, if we tried take an inner product between the first and the second vector, we would see that we get 0 plus 0 plus 0 equal to 0, which means they're orthogonal. And in fact, if we were to calculate the inner products between all 3 vectors, we would see that they're all orthogonal with one another. The first and the third are also orthogonal. And since we stated on the previous slide, right, that orthogonal vectors are by default linearly independent, this means that this set of vectors is linearly independent. Now, this third example is actually very similar to the example I gave you, in which we have a set of orthogonal a set of vectors which are not orthogonal, but which are in fact linearly independent. And why is that? Well, again, if I take a times 1, 0 plus b times 1, 2, set them equal to 0, 0, I'll get the vector a plus b, 2b equal to 0, 0. So this gives us a system of equations, right? A plus b equals 0, 2b equals 0. So from this equation, we know that b equals 0. So, and then from this equation, a plus 0 equals 0. So a must also equal 0. So the only solution for which this original equation holds is if both a is equal to 0 and b is equal to 0, which means that there's no possible sort of combination, or I guess scalar multiplied by the first one or scalar multiplied by the second, which results in the other. Thus, these are linearly independent. I guess more intuitively, an easy way that we could have explained this is that we had a 0 in the second component, so there's really no scalar that we could multiply by this first vector so as to get the second vector, because of course there's no scalar we can multiply by 0 to get 2. Alright, so hopefully that clarified the idea of linear independence. Now we're going to have a discussion about the notion of span. And linear independence and span are both very important for the concept of basis, which we'll get to right after this. So to define span, essentially we have to refer back to our notion of vector space. We have a vector space V, and if that vector space consists of all possible linear combinations of a set of vectors W1 through Wk, then we say that those vectors span the vector space V. And so I wrote that in some other words below, but I think that this concept is probably best illustrated through an example. So, for example, if our vector space is equal to R3, the set of all possible three-dimensional real vectors, we can define a set of vectors, v1, v2, v3, or w1, w2, w3, as follows. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And these vectors span the vector space R3, because if we took A times 1, 0, 0, B times 0, 1, 0, C times 0, 0, 1, we'd get the vector A, B, C, where A, B, and C are real numbers. And since we could set A, B, and C to be any possible real number, this vector allows us to create any possible vector in R3, and thus, all right here, this spans R3. Now, I could have added actually more vectors to our set, and it still would have spanned R3. So I could have also defined the set 1, 0, 0, 0, 1, 0, 0, 0, 1, and then maybe thrown in the vectors as well, 1, 0, negative 1, 2, 10, 4, and so forth. And we would still say that these vectors span R3, right? Because these first three vectors allow us to create any possible vector in R3. We could also probably from this set of vectors create any vector in R3 and so forth. So basically the idea of span is just that from a set of vectors, we can create any possible vector in the space. And you could have the set of vectors. So for example, R3 spans R3, right? From the set of all possible vectors in R3, I can create all possible vectors in R3. That's true, but it doesn't really help us much. So in the next slide, I'll be introducing the notion of basis, which is where things really get interesting. And so a basis is basically a minimal set of vectors which spans our full vector space. So let me write that out. Minimal set of vectors to span our vector space. And so then how do we go about defining a basis? Well, it's a balance between the two properties we just discussed. So the set of vectors in a basis must all be linearly independent, but they must also span the set V. So our linear independence is what imposes that it's a minimal set, whereas of course our span is what enables us to span the whole vector space. And the reason why I wrote that if the vectors are linearly independent, that constrains us to not too many vectors is, right, remember in our examples that we were looking at, we saw that, for example, in 2 dimensions, we could have 2 vectors that were orthogonal or 2 vectors that were linearly independent. And it turns out that if you want your set of vectors to be linearly independent, this implies that the number of linearly independent vectors actually has to be less than or equal to the dimension of your vector space. Whereas when you want to span a full vector space, the number of vectors that you need in your set has to actually be greater than or equal to the dimension of your vector space. So on this previous slide, we saw, right, that 1, 0, 0, 0, 1, 0, 0, 0, 1 all span the vector space R3. If you were to remove any one of those vectors, you wouldn't be able to create any possible vector in R3, right? You might, you would just end up with a term that always had to be 0. And of course, if you took a linear algebra class, you would learn more formally why these are true. But for now, just sort of take our word for it. And so basically, having linear independence while still spanning our whole vector space means that we have to follow these 2 constraints. Thus, putting this together, this means that the number of vectors in our basis must actually be equal to the dimension of our vector space. So if someone comes to you and asks whether their set of vectors is a basis for some vector space, one easy way that you can check right off the bat is just seeing whether the number of vectors in the basis is actually equal to the dimension of the vector space. And if it's not, you can right away tell them that they don't actually have a basis for their vector space. So one other important thing to note about bases is that every vector in the vector space is a unique linear combination of those basis vectors. So since those basis vectors allow us to span R3, right, the definition of span is that we can create any possible vector in R3. But since it is a minimal set, that also means that every vector in the vector space can only be created through a single linear combination of the vectors in the set. If the vectors weren't constrained to be linearly independent, then there could potentially be multiple linear combinations of the vectors that you could then use to create the resultant vector. One other important thing to note is that every vector space has infinitely many distinct bases. So infinitely many. But remember, each of these bases are still the number of vectors in the basis is still equal to the dimension of the vector space. So we have infinitely many possible bases, infinitely many sets of basis vectors that can form a vector space. That can form a basis of a vector space. And I'll give a sort of intuitive picture as to why this is the case. So you have, let's look at, for example, the vector space R2, for which we already said a possible, or for which we have a possible basis 1, 0, 0, 1. Let's start off by checking why this set of vectors is a basis for R2. Well, first, let's check the idea of linear independence. We already saw, right, that these vectors are orthogonal. So we get that they are linearly independent because they are orthogonal. Now for the notion of span, right, if we take a times 1, 0 plus b times 0, 1, that gives us the vector ab, which allows us, assuming a and b can be any possible real number, to create the set of all possible two-dimensional real vectors. Thus, this set of vectors spans R2. So, since this set of vectors both are linearly independent and span R2, it must form a basis. Now, geometrically, what does this set of basis vectors look like? Well, it looks like this. Earlier in the class, we actually referred to them as x hat and y hat. And so geometrically, right, if I were to scale these vectors and add them together, I could create any possible vector in R2. All right, but now why is it necessarily true that every vector space has infinitely many bases? Well, geometrically, right, if I was to take this vector space and rotate it, let's call this x hat prime, y hat prime, that doesn't change the orthogonality condition, right? These vectors are still orthogonal, thus still linearly independent. And further, the fact that I rotated these vectors doesn't change my ability to span the full space, right? I could still create any possible vector in the space by taking a linear combination of these two vectors. And again, I'm not defining any of this rigorously. If it doesn't make perfect sense to you, just take my word for it. Furthermore, I could scale my original basis vectors. So for example, shrink my y hat vector to make y hat or y double prime, and elongate my x vector to make x double prime. And once again, right, scaling my vectors doesn't change their orthogonality, and in order to span my whole space, nothing would change other than the fact that my coefficients in my linear combination would be modified. So what does this tell us? Since we can rotate our basis any possible way, as well as scale our vectors, or even both rotate and scale these vectors, they're still a basis for our space. And since we can perform infinitely many rotations or infinitely many scaling of our vectors, we can create infinitely many bases for our vector space. And with that, here I have a practice problem for you guys to try out. Again, since you're watching video, please pause here to take a stab at it. Otherwise, I'll go through the solutions myself now. So, to go through this first problem here, we see that we're looking at the vector space of R2, and these vectors actually look familiar to some vectors we already said were a basis, right? If we were to take -1 times 1, 0, and 7 times 0, 1, we would get these two vectors, right? And what did I say on the previous slide? Scaling preserves. If we have a set of basis vectors and we scale our basis vectors, they're still a basis. So this is in fact still a basis. Now, in this second example, we're looking at R3, the set of three-dimensional vectors, but we see right off the bat, right, that we only have two vectors. So our number of vectors is equal to 2, which is less than 3, which is the dimension of our vector space. Thus, right off the bat, we know that it cannot be a basis. But let's dive a little bit further into why not. Well, if we were to take arbitrary coefficient, multiply it by the first vector, take another arbitrary coefficient, multiply it by the second, we would get that we have the vector a, b, 0. However, we know, right, that if we have a basis, we need to be able to create any other possible vector in our vector space through a linear combination of those basis vectors. So we have here our linear combination, but we see that the final entry in our linear combination is 0. So if we wanted to, for example, go and try and create the vector 1, 3, 4, well, this wouldn't be possible, right? Because using only these two vectors, the final entry of any vector we can create is constrained to be 0. Thus, this isn't possible, meaning that this set of vectors doesn't span the vector space. I'll just write R3. All right, and so finally, moving on to example number 3, we're now looking again at the vector space R2, but we see right off the bat that the number of vectors in our vector space, or in our possible basis, is 3, which is greater than 2, which is the dimension, right, of R2, the vector space that they lie in. So, again, using our rule that the number of vectors in our basis set must be equivalent to the dimension of our vector space, we can tell that this is not a basis. And let's see why not. Well, if we had -1 times our first vector plus 1 times our second vector, we would actually get the vector -1, 1, which is the third vector in our set, meaning that this vector can be expressed as a linear combination of the first two, meaning that the vectors in our proposed basis set are not linearly independent, which means that they are linearly dependent, right? And again, for us to have a basis, all of the vectors in our set must both span the vector space while being linearly independent. So hopefully working through these examples helped clarify things a bit. And before we move on to our discussions of eigenvectors and eigenvalues, I just wanted to clear up, I guess, a definition notational thing that frequently pops up in quantum computing. So in quantum computing, rather than hearing people use the term vector space, you'll often hear them say Hilbert space. And if you don't have a really advanced background in linear algebra, off the bat, this might sound scary and more complicated than a vector space. However, it's really not much more complicated than what we've described so far. And in fact, a Hilbert space, although it has a very rigorous mathematical definition, for all intents and purposes in our case, is just a vector space equipped with an inner product. And now, what do I mean by that? So for example, if you have the vector space C2, two-dimensional complex complex vectors, you can, so this is our vector space. You can define a basis set for it. It follows the axioms of vector spaces, but it also has a notion of inner product defined for it. So all of the vector spaces follow our definition of inner product that we've previously talked about, right? Where you have vectors u and v, which line the set, and in the vector space, you can take the complex inner product, which in Dirac notation we write as uv. And why, you might be wondering, okay, why does this matter? What does matter if I can perform an inner product on vectors in my vector space? Well, we already saw, right, that the inner product is a super useful tool for determining things like orthogonality, right, and those sorts of things. It also allows us to define a notion of vector norm. So if I have some vector in the vector space, I can define the vector norm as the square root of the inner product. And it also allows me to normalize my vectors, right? These are all things that we saw previously in our linear algebra lectures, and these are all very relevant to quantum computing, right? Because in quantum computing, our vectors are representing quantum states, and the components of our vectors are actually probability amplitudes of measuring our state along different axes. And we already saw, right, in our probability unit that all probabilities must sum to 1, meaning that the components of our vectors must be normalized. So there's a lot of really important physical properties that necessitate us having a definition of an inner product and being able to normalize, which is why it's so important that our vector space is in fact a Hilbert space. That being said, there are vector spaces which in fact are not Hilbert spaces, but for the purposes of this class, we aren't too concerned with that. And I guess in general, we will actually be working with Hilbert spaces. But this is more so if you just go and read maybe a paper or some textbook out in the field. Don't be intimidated by the term Hilbert space. It's really not much more complicated than what we've learned about so far in the class and in this lecture. And then I just wanted to conclude this section by reviewing some questions that students had in the live lecture recording. So I think that there was still some confusion. So these are two separate questions that students asked in the live lecture recording that I answered. So the first question students had was still some confusion on the relationship between a vector space, basis, linear independence, and span. So just to walk through it here again, you have some vector space V, which has a basis defined. And this basis must be, all of the vectors in your basis must be linearly independent, and the basis spans the full vector space. So what does this mean? Basically, all of the vectors in your basis are independent of one another, but can be used to create any possible vector in your vector space. Remember again that a basis is a minimal set of vectors which span your vector space. So hopefully that clarifies that a little bit. The second question that we got, again, was sort of some confusion about the notion of how you can have infinitely many bases. But for example, in R3, all bases only have 3 possible vectors. So I think the student was confused when I said that a vector space can have infinitely many bases, since I had also said that each basis could only have the number of vectors equivalent to the dimension of the vector space. So to clarify that question, I brought up the example of R3, for which we can define the basis 1, 0, 0, 0, 1, 0, 0, 0, 1 here, right? Which in our geometric picture looks as follows. You have 3 orthogonal vectors. Well, I could perform, right, any scaling of this basis, and that would still constitute a basis, but each possible basis I create still only has 3 vectors in it. So in this case, I multiplied the first basis vector by 3, the second by 4, and the third by 7. And this still constitutes a basis, but note that there's only 3 vectors in it. I could alternatively, geometrically, rotate my set of basis vectors, and I would still have a basis, but again, there's only 3 vectors in this basis. That being said, there's infinitely many possible set of bases, so infinitely many possible sets of 3 vectors like this, or geometrically pictured like this, that I could create, which are still valid bases for my vector space R3. So hopefully if you had some confusion about that statement, that clarifies it. If there's still any questions, make sure to post on Piazza or ask in your recitation sections or lab sections. All right, and with that, we're going to move on to the notion of eigenvectors and eigenvalues. I will pause my video and come back after a quick break. You can also feel free to take a quick break if you need to. All right, everyone. So Now that we took our break, we're going to dive right into eigenvectors and eigenvalues. Once again, these are super important concepts for engineering, physics, and science, and I'm sure you'll encounter them later on in your STEM career, even if you don't end up in quantum computing. But for quantum computing, they're also specifically super important, and we'll start to see why through some examples we work through in the rest of this lecture. So I wanted to start off by sort of defining conceptually and geometrically what exactly an eigenvector and eigenvalue are. So typically, when you multiply a matrix by a vector, the resultant vector is both a scaled and rotated version of the original vector. And as an example, let's perform this matrix vector multiplication. So we get -8 plus 10, 8 minus 3, it's 2, 5. So if we draw our original vector, which is 8, 1, and our resultant vector, which is 2, 5, we can see, right, that we both rotated our vector, and the length of our new vector is a bit shorter than our original one, so we also shrunk or scaled it. In the case, however, when a matrix is multiplied by an eigenvector, its eigenvector, the resultant vector is only scaled, so there's no rotation whatsoever. And to see an example of this, I put two examples of this matrix, 6, -1, 2, 3, being multiplied by its eigenvectors. So that's the first eigenvector, 1, 1. Second eigenvector is 1, 2. And in performing the multiplication, we'll see that this is equivalent to 6 minus 1, 2 plus 3, 5, 5, which is simply just 5 times 1, 1. 5 being a scalar multiplied by our original vector. So we see here we'd originally multiplied our vector by a matrix, but in essence, this boiled down to simply just multiplying the vector by a scalar coefficient. In the second example, we have 6 minus 2 and 2 plus 6, which is 4, 8, which is 4 times 1, 2. And so once again, we multiplied by a matrix, but at the end of the day, this just boils down to taking our original vector and multiplying it by 4. So geometrically, if we were to look at things, our original vector in the first case was 1, 1. Our original vector in the second case was 1, 2. After we multiplied by our matrix, we got the resultant vectors 5, 5, and that's 4, 8. So we can see that this matrix multiplication essentially only elongated our vectors. And the scalar factor in front of our vectors, this term of elongation, actually has a special name. This is called the eigenvalue, which corresponds to the eigenvector. And so we'll see that every matrix, every square matrix, has at least one distinct eigenvector eigenvalue pair. Usually a matrix will have multiple eigenvectors, and each eigenvector has a corresponding eigenvalue, which is the scaling coefficient. Now, in quantum computing, this is really important because it turns out that these eigenvectors are related to our measurement axes, which in actual quantum physical systems can correspond to things like spin and the orientation of our atoms, depending on which platform you're using for quantum computing. This will have different physical interpretations. But typically speaking, the corresponding eigenvalues for each of the eigenvectors corresponds then to the energy of your system when it's in that state, or if we're looking at quantum measurement, the likelihood of measuring your qubit either in the 1 or 0 state along a certain measurement axis. And we'll see a bit more of that soon. But before we get to that, let's go through a bit more of the math. So just to kind of formalize what we've already seen, you might ask, why do these notions of eigenvectors matter? And in the case of an eigenvector, our matrix vector multiplication simplifies to just a scalar vector multiplication. And so in the blue box, I've written sort of the key equation you should keep in mind when you think about eigenvalues and eigenvectors. So you have some matrix A, and that matrix A will have at least one eigenvector. So let's label these eigenvector. And for each eigenvector, you'll have some scalar coefficient, lambda, which is its eigenvalue. Now, you might be wondering why we keep throwing this eigen prefix in front of everything. And it turns out that in German, the little phrase eigen actually means proper, characteristic, or ohm. And this sort of goes back to what I was just saying in terms of physics, engineering, and quantum computing. Usually the eigenvectors are sort of key things about our system. So if our matrix A is a representation of some physical system that we're interested in, usually the eigenvectors correspond to important either energies or frequencies or axes relative to our system. Each matrix will only have a few eigenvectors, usually. It's not, if you were to randomly select a vector, it's not likely that you would just select an eigenvector of a matrix. But usually the eigenvectors are pretty important in terms of defining the characteristics of your system. And we'll gain some more intuition for this, especially in second semester, when we actually begin looking at all of these mathematical concepts in more of an applied context. But for now, we want to just learn the math so that later on we can really focus on the physics behind everything and be comfortable with eigenvalues and eigenvectors. So with that, I have an example problem for you guys all to practice on. Make sure to stop the video and try and work this out yourself before we go into it. But basically the question is asking us whether the following vectors are eigenvectors of their corresponding matrices, and if so, what is the eigenvalue corresponding to these eigenvectors. So let's work through the solutions to these. Basically, to check if the vectors are actually eigenvectors of our matrix A, we'll just multiply the matrix by the eigenvectors and see if it is equivalent to actually a scalar multiplication. So we have 0, 1, -2, -3 times 1, -1. And this is 0 minus 1, -2 plus 3, -1, 1, which we know is just -1 times 1, -1. So, since it does boil down to a scalar multiplication by our original vector, we know that it is in fact an eigenvector with eigenvalue of -1. Now let's move on to our second example. We have 3, 1, 4, -3, 1, 0, which is just 3 plus 0 4 plus 0, 3, 4. Now, since our original vector had a 0 in the second component, there's nothing we can multiply by 0 to get 4, right? So we know that, in fact, this vector is not a scalar multiplication. This vector, there was some rotation performed in addition to scaling. So we say that this is not an eigenvector. All right, so hopefully that gives you guys some intuition for a bit more of the mathematics. I now wanted to walk through the steps of how you can actually go about calculating the eigenvectors and eigenvalues of a matrix. Do note, however, that for the purpose of this class, we won't actually be expecting you, when we get to the actual quantum mechanics, to calculate out the eigenvectors and eigenvalues. That being said, this is like a pretty important thing that you'll oftentimes learn in linear algebra, and it doesn't take too long to go through, so I'll walk through it really quickly at a high level. If you feel like you don't understand it, that's all right. You can use online calculators to calculate the eigenvectors and eigenvalues of matrices. You're also now all familiar with Python. There's ways to calculate eigenvalues and vectors of matrices pretty easily in Python. So if this doesn't make total sense to you, that's fine, but I still encourage you to watch because it's pretty cool. So we'll start off with our key eigenvector eigenvalue equation. We have our matrix A, and we want to figure out what the eigenvectors and eigenvalue of the matrix are. So we'll do a bit of manipulation. We have A, V, and we can stick an identity matrix after our lambda. Remember, of course, that the identity matrix, depending on the dimension of your matrix, is just a bunch of 1s and 0s. 1s along the diagonals, 0s on the off diagonals. Now, if we move everything to the left side, we get AV lambda IV equals 0. We can factor our terms, and so we get this expression. Now, we want to solve, remember, for these two terms. Let's, for ease of notation, say that we have some matrix B, which is then equal to A minus lambda I. So we can rewrite this equation as BV equals to 0. So there's two possible solutions to this system of equations. The first, right, is the trivial solution. B is invertible. And if B is invertible, we have BV equals 0. We multiply by B inverse, which then gives us that V is equal to B inverse times 0, which of course just tells us that V is equal to the 0 vector. This, however, isn't interesting, right? Of course, when you multiply a matrix by the 0 vector, that's equivalent to just any scalar multiplied by the 0 vector. This is really an uninformative solution. So, in order to avoid the trivial solution, we want the case that our matrix B is not invertible. Since we saw that when it was invertible, we did get a trivial solution. So for the non-trivial solution, B is not invertible. And the linear algebra term for saying a matrix is not invertible is that B is singular. And there's a way mathematically to calculate whether or not a matrix is singular. It turns out that there's this operation called the determinant. B determinant. And so if the determinant is equal to 0, that implies that B is singular, and vice versa. If B is singular, then the determinant is 0. So if we impose this restriction, we can then solve for what the eigenvalues and then the eigenvectors of our matrix should be. For those of you who haven't taken a linear algebra course or might not be familiar, the determinant is an operation which takes your matrix and calculates out a scalar value, and this scalar has a bunch of special properties, including that it can determine whether or not your matrix is singular. If you take a linear algebra course, you'll learn a lot more about it, but for now, you should just note that the determinant of a 2x2 matrix is defined as followed. It's just AD minus BC. So multiply across and subtract the other multiplication across. And we'll be using that in the next few slides to actually go about calculating the eigenvalues and eigenvectors of our matrix. So let's start off by calculating the eigenvalues of our matrix negative 6, 3, 4, 5. And as we just derived on the last slide, so in this case, this is our matrix A, determinant of A minus lambda I is equal to 0, then we can solve for this parameter lambda, which are our eigenvalues. So let's plug things in and actually go about solving this. So we have determinant of negative 6, 3, 4, 5 minus lambda 0, 0, lambda. And if we put that as one matrix, we'll have negative 6 minus lambda 3, 4, 5 minus lambda. And remember on the last slide, we said that the determinant is the product of these minus the product of these. So we get that negative 6 minus lambda times 5 minus lambda minus 12 is equal to 0. And so if we go and we just do some algebra, we can solve this system of equations. This gives us an so we have lambda squared plus lambda, and that's 42. We use our algebra skills from high school to factorize this. We get, I think I messed up my signs here. All right, so now that we have a factorized equation where lambda plus 7 times lambda minus 6 is equal to 0, we know that if lambda equals negative 7 and 7 will become 0, and our equation will hold true. Or if lambda is equal to positive 6, it will also hold true. We know that lambda can be equal to either negative 7 or 6. All right, so now we have the two eigenvalues. I just wanted to make a more general note as well that this expression here is sort of oftentimes referred to as the canonical equation of eigenvalues and eigenvectors. You'll always find that regardless of the size of the matrix, you'll end up getting an expression where you'll have lambda So when you're solving for the eigenvalues of your matrix, you'll always get an expression of this form where you should have as many eigenvalues as the dimension of your matrix. In this case, we had 2 eigenvalues because we have a 2-dimensional matrix. But what you might find sometimes is that you'll have repeated eigenvalues. So your eigenvalues don't necessarily need to be distinct. All right, so now that we've solved for the 2 eigenvalues, we can actually solve for the 2 corresponding eigenvectors by plugging our eigenvalues back into our original system of equations. So let's start off with our eigenvalue that lambda equals -7. And so we had our original system, right, that AV equals lambda v, which implies A minus lambda I v equal 0. And so now we can plug back in our eigenvalues, which we just solved for here, to solve our system of equations. So let's go about that now. We have -6 plus 7, 3, 4, 5 plus 7 times v1, v2 equal 0, 0, which then gives us 1, 3, 4, 12, v1, v2 equals 0, 0. And that gives us the system of equations v1 plus 3v2 equals 0, 4v1 plus 12v2 equals 0. We see that these equations are just scalar multiplications of each other. The second equation is just 4 times the first equation, which means we can pick whatever value we want for v2 and then solve for v1. So if we set v2 to be 1, then by the first equation here, we know that v1 must then be -3. So this is eigenvector of A with eigenvalue -7. And moving on, we can now solve as well for our second eigenvalue, which is 6. And we can solve again similarly. So we'll have -6 minus 6, 3, 4, 5 minus 6. And that gives us 12, 3, 4, -1, v1, v2 equals 0. So we'll get the system of equations, -12, v1, 3, v2, 0, 4, v1 plus, minus v2 equals to 0. So if we set now v1 to be equal to 1, then that means that v2 must be equal to 4. And so this is the eigenvector of A with eigenvalue 6. And what does that mean? Well, if we multiply -6, 3, 4, 5 by 1, 4, we should see that that's equal to 6, 1, 4. I'll have you guys do that on your own and check for yourself. Hopefully I didn't make any calculation error here, but it should be true. All right, so now that we've seen how you can actually go about calculating an eigenvector and eigenvalue, remember, you can also do this easily on a calculator. Let's explore a bit further what the actual meaning is of an eigenvector and eigenvalue in the context of quantum computing. So I hinted at this a bit earlier, but now that we know a bit more about eigenvectors and eigenvalues, we can explore things in a bit more depth. Last class, Amir taught you about the 3 different types of Pauli matrices, Pauli X, Pauli Y, and Pauli Z, which correspond to rotations right around the block sphere. But as it turns out, the eigenvectors of these Pauli matrices actually correspond to our measurement axes. And when we perform measurements on a true quantum computer, depending on what physical platform we're using, we oftentimes will measure along the z-axis or in some cases along the x-axis. But as I hinted at before, the eigenvalues essentially tell us sort of in which direction we're more oriented, which then determines the probability or likelihood of measuring a state along that axis. And of course, in second semester, we'll actually go through this all rigorously, but today I wanted to walk through the math a bit and prove to you all that the eigenvectors of the Pauli matrices are actually eigenvectors. So I'm just going to tell you guys off the top, like I've pre-calculated for you all what the eigenvectors are of the Pauli matrices, and we're just going to work through and confirm that they actually are eigenvectors. And remember, we can do this just by simply performing out the multiplication. So in this case, I have the Pauli X matrix. If we multiply 0, 1, 1, 0 by the x plus eigenvector, which is 1 over square root 2, 1 over square root 2, we see that we get 1 over square root 2, 1 over square root 2. So this is an eigenvector with eigenvalue plus 1. Now, if we multiply the Pauli X matrix by the second eigenvector, which is 1 over square root 2, negative 1 over square root 2, we see that we get negative 1 over square root 2, 1 over square root 2, which is equal to negative 1, 1 over square root 2. So this is instead an eigenvector with eigenvalue negative 1. And you can see, right, that in the case of the plus 1, we denoted that eigenvector with a plus subscript, and in the case of in the case that we got the negative 1 eigenvalue, we denoted that eigenvector with a negative sign. And so we'll have similar things happen for Pauli Y and Pauli Z. For the sake of time, I'll just write out that this has eigenvalue plus 1 as well, and this has eigenvalue minus 1. I encourage you, though, to go through yourself, work through the math, and try and confirm it on your own. In the case of Pauli Z, we have the same thing, eigenvalue plus 1 and eigenvalue minus 1. Now, you can see here, right, that the eigenvectors of our Pauli Z matrix actually look pretty similar, right, to our definition of a basis for the vector space R2 or C2. And it actually turns out that all of these eigenvectors are bases of our quantum vector space, which is kind of what I have here on this slide. In the case of Pauli Z, it's pretty self-evident, right? We've already seen that this is a basis of R2, of C2, and that's pretty clear. For the other vector spaces, I'll just have you guys take for granted that the eigenvectors of span the quantum vector space. We're not going to go into detail today about what exactly the quantum vector space is, so just take my word for it that they do actually span the quantum vector space. We'll learn a lot more about this in second semester, but since we already have some practice with orthogonality and inner products, I did want to work through a bit the notion that all of these the eigenvectors are linearly independent of one another. So we have yx plus inner products of these are all equal to 0, meaning that the eigenvectors are orthogonal, and we can do quick checks of that, right? So in the case of the poly X matrix, this is 1 over square root 2, 1 over square root 2, 1 over square root 2, negative 1 over square root 2 is equal to 1/2 minus 1/2 equal to 0. In the case of poly Y, we have 1 over square root 2, negative I over square root 2. And remember, we are taking our complex conjugates, so we actually also get negative 1 over square root 2. Even though this is plus, this becomes minus because we're doing a complex conjugate. And so we get 1 over 2 plus I squared over 2, which is just equal to 1/2 minus 1/2 equal to 0. And then, of course, 1, 0, 0, 1 is just 0 plus 0 equal to 0. So we can see that all of these vectors are orthogonal, which implies that they are linearly independent, which means, so combining the fact that they both span the quantum vector space and are linearly independent, they then form a basis. So we have 3 separate bases. We have the bases of the which consists of the 2 poly X eigenvectors. We have the basis which consists of the 2 poly Z eigenvectors, and we have the basis which consists of the 2 poly Z eigenvectors. And these are all valid bases, and depending on which frame of reference we want to look and orient ourselves in, we can pick a different basis for our quantum vector space and thus all of our quantum operations and measurements. And so this is a really important and powerful tool in quantum computation. And a lot of what we'll be doing next semester is actually just calculating out, manipulating eigenvalues, and playing around with these eigenvectors. One other thing that I wanted to note is, again, and remind you, based off of what we learned earlier in the lecture, right, is that since these eigenvectors form a basis for the space, this means that any vector in our quantum vector space can actually be expressed as a linear combination of the eigenvectors of a single poly matrix. So for fun, let's decompose the poly plus eigenvector, the poly X plus eigenvector, 1 over square root 2, 1 over square root 2, in terms of our poly Z eigenvectors. So this is equivalent to 1 over square root of 2, 1, 0, plus 1 over square root of 2, 0, 1, which then is 1 over square root of 2, yz plus 1 over square root of 2, yz minus. And then, of course, right, if we wanted to multiply our poly z operator by this poly x eigenvector, our poly z matrix being 1, 0, 0, negative 1, we would get that, sorry about all the typos. They always say math is a lot harder when you're teaching, and it's quite true. So you would get this resultant vector, but alternatively, we could also look at it from the perspective of taking our poly z and then multiplying it by 1 over square root 2, 1, 0, plus 1 over square root 2, 0, 1, which we know then is 1 over square root 2, poly z, 1, 0, plus 1 over square root 2, poly z, 0, 1. And remember that this matrix then, when multiplied by its eigenvectors, boils down to a scalar multiplication. So we know that this is our this first one here is our plus eigenvector. So that gives us a multiplication by plus 1, and the second one is actually a multiplication by negative 1. So we get ultimately 1 over square root 2 is 0, plus 0, negative 1 over square root 2, 1 over square root 2, negative 1 over square root 2. And so we see the two results are the same. In one case, multiplying by the poly x or poly z matrix performed a rotation, but in this case, in which we decompose the poly x matrix according to the poly z basis vectors, we instead perform two sort of scalar multiplications. And again, this is sort of just taking everything we learned in a lecture and looking at it from the perspective of quantum computing. Next semester, of course, we'll actually get to see the physical meaning and interpretation behind all of this. I think I added an extra slide. But ultimately, all of this is super important for calculating probabilities of measurement along the different axes of the Bloch sphere. And ultimately, quantum computing is clever manipulation of your eigenvectors and bases. So these are all super important concepts. Make sure you do your homework, get plenty of practice with this over the winter break so that you can be well prepared to play around with things next semester. Now, speaking of next semester, I just wanted to conclude today's lecture by giving you all a taste of what's to come next semester. Make sure you're all hyped, thinking about and excited about quantum over the winter break as we enter second semester. We are going to be giving you a crash course in quantum computation and quantum information, which should be super exciting and is equivalent actually to the introductory quantum computing class that Amir and I took and taught at MIT. So you guys will be really well prepared and in a good state to then either read more books and papers on your own or even work on cool projects and potentially start doing research in the field. We'll also next semester have a component of a final project in which you'll get to explore an application or topic that you are particularly interested in more depth. But I guess just to sort of look back on what we covered this semester, we basically covered a lot of math, right? We did an introduction of probability, linear algebra, complex numbers, which are all super important STEM topics and all super relevant in the domain of quantum computing and quantum information. However, it was very math heavy, and we did try to give you a flavor and foreshadow what was to come in second semester by relating things to quantum computation and information. But next semester is when we're going to really get into all of the quantum fun. So we'll start off next semester with a quick review of all the math, make sure you didn't forget anything over winter break, and then we'll dive into a 3-week introduction crash course on quantum mechanics. We'll then move on to quantum information, quantum protocols, quantum algorithms, experimental quantum information processing, and quantum applications, research, and more. So in the next 10 minutes or so, I'll just give you a bit more detail as to what I mean exactly when I say we're going to be covering each of these topics. So when we talk about quantum mechanics, our key objective is going to be answering the question, how does physics work at the microscopic or quantum scale? And we'll mostly go through this by looking back at some of the key experiments from which quantum mechanics theory was developed. So the first one is the photoelectric effect, which actually Albert Einstein won his Nobel Prize for, which was basically an experiment which demonstrated the discretization of energy, in which we actually think of light as photons instead of waves, continuous waves. The double slit experiment was kind of the opposite. In that experiment, we realized that matter can actually act as a wave instead of just as a particle. And so you get, between these two experiments, you get the notion of wave-particle duality, if you've heard of that before. If not, don't worry. We'll learn all about what that means next semester. The final experiment we're going to cover is the Stern-Gerlach experiment, which tells us that actually the angular momentum at the atomic scale is quantized. For those of you who might have taken chemistry in high school, this is related to the notion of spin, for example, of your electrons, and is actually super relevant to measurement in quantum computation and information. We'll also run through all of the postulates of quantum mechanics, and from those basic postulates, you can derive essentially all of quantum mechanics theory. And then finally, we'll be going into more depth into quantum entanglement, doing some more advanced mathematics behind it, and really concretely and formally explaining what exactly quantum entanglement is, since it's such a weird phenomenon. Once we have the basics of quantum mechanics down, we'll move into quantum information, and that's answering the question, how can information be stored and manipulated in quantum systems? We've actually previewed quite a bit of this in this semester. We've already introduced to you guys the qubit and the block sphere. Last lecture, Amir talked quite a bit about quantum gates. When I did my section on probability, we introduced you guys a bit to the notion of quantum measurement. But in this unit, we'll really be piecing all of those things together to show you how you can construct quantum circuits. And in quantum computation, and more generally in quantum information, you use quantum circuits in order to manipulate qubits and thus do quantum information processing. Once we've learned how to build quantum circuits, we'll use those quantum circuits to actually build up protocols, trying to answer the question of how quantum systems can be used to safely and efficiently transmit information. We'll study 3 really, really cool examples of quantum protocols. The first is one of my personal favorites, the BB84 quantum key distribution protocol, which basically was actually the first quantum cryptography protocol, and it's a method for securely communicating a private key. Now, when I say a private key, you can think of a private key as like a one-time password that you use to open a communication channel between 2 people. Now, it's really important that you're able to transmit a key safely to someone else and ensure that no eavesdropper was able to intercept it, because if the eavesdropper intercepts on this key, they can listen to all of your communications, which were meant to be encrypted. So that's a really fun one. We'll also cover super dense coding, which is a super cool quantum protocol which enables you to transmit 2 classical bits of information with one quantum bit, so 1 qubit. That's why it's called super dense. You're basically condensing 2 bits of classical information into 1 qubit. Now, finally, we'll cover quantum teleportation, which is Kira's personal favorite, which is literally just a way of teleporting quantum information from a sender who is at one location to a receiver at another. Oh, and then I guess here I drew the actual circuits out, and by halfway through next semester, you'll actually be able to see why these circuits correspond to super dense coding and quantum teleportation. So get really excited to master quantum circuits. So after we do quantum protocols, we'll move on to quantum algorithms. And in this section, we're going to answer the question, how can quantum systems provide an advantage to classical systems for computation? When you hear about quantum computers, this is usually what people were referring to. We want to develop quantum algorithms which can outperform any classical algorithms that we have today. And we'll study 4 key quantum algorithms. The first is the Deutsch-Jose algorithm, which was actually one of the very first quantum algorithms that was proven to have an exponential speedup over classical algorithms. Now, as an algorithm itself, it's not particularly useful. It just solves the simple toy problem of determining whether a function is constant or balanced. Constant meaning that it has a 0 for all outputs or a 1 for all outputs, whereas balanced means it has a 0 on half of the outputs or a 0 on the other half. So we look at Deutsch-Jose just as an introduction to algorithms, and because historically it was one of the very first to give an exponential speedup. After we cover Deutsch-Jose, we'll move on to VQE and QAOA. So QAOA stands for Quantum Approximate Optimization Algorithm, and this is actually a hybrid quantum classical optimization scheme in which you encode part of your algorithm on a quantum computer, and then you encode the other part of your algorithm, which usually is some sort of optimizer on your classical computer. The idea being that when you add the quantum simulator to your standard classical optimization algorithm, you can actually get a performance increase or a speed up in your algorithm runtime. And optimization problems are everywhere in the real world, and oftentimes some of them are usually some of the hardest problems to solve. So if you can get an advantage in optimization, that's a really big deal. QAOA is actually a pretty active area of research right now. So this is starting to get into really state-of-the-art stuff. We'll also look at VQE, the variational quantum eigensolver algorithm, which is also a quantum classical hybrid algorithm. The key difference in this case being that instead of performing an optimization, you're actually solving for the eigenvalues, most frequently the minimum eigenvalues of a quantum wave function or quantum, which basically then corresponds to finding the minimum energy state of your system. Note here that we have, again, our nice eigen prefix. So, again, pointing at how the material we covered this lecture was pretty important. This algorithm is dedicated just to finding eigenvalues of your system. And it turns out that this is pretty important in the context of chemistry. There's a whole field of quantum chemistry in which this is particularly important, because if you have some molecule, it is usually pretty important to be able to know what the lowest energy state of that molecule is. And this has all sorts of applications then to medicine and other fields. So again, VQE is also a very hot topic right now in research, really cutting edge stuff, and you will understand it all by the end of this class. Now, the last algorithm we're going to cover is also a historic algorithm, but one of my personal favorites. It's called Grover's algorithm, and it gives a quadratic speedup for database search. So database search is a pretty important problem. Basically, if you have a list of items and you're trying to find a particular item in that list, how can you do it? Well, on a classical computer, your runtime is O of n. You have to usually search across all the items in the list, because if your item is the last item in the list, you'll only reach it by getting to the end. But Grover's algorithm uses a clever manipulation of quantum and a neat property called amplitude damping that we'll learn all about to actually make it so that you can find items in a database in O of square root n time instead of O of n. So this is a super cool algorithm, and it has a really nice, fun visual interpretation, which is personally why I like it a lot. So yeah, that's the last key quantum algorithm we'll cover. Once we finish getting through the more theoretical stuff, we'll also give you guys a flavor of the experimental side of things. So for our experimental quantum information processing unit, we'll begin by asking and answering what physical platforms are we trying to build quantum computers with. As you know, we don't currently have full quantum computers that we can just go and run any quantum algorithms on. David gave you a lab tour of Professor William Oliver's group, which is one of the leading leaders in the field of superconducting quantum computers, and even in that group, they only have systems on the order of tens of qubits. The best quantum computers in the world to date, run by IBM and Google, have on the order of 50 qubits. But in order to run these really big quantum algorithms, ideally we would want qubits that have thousands, if not hundreds of thousands, of fault-tolerant qubits. That being said, though, while most companies and a lot of research groups are using superconducting qubits, there's all sorts of different platforms that you can actually use for quantum computation, including nuclear magnetic resonance, trapped ion, Majorana and topological qubits, diamond NV centers, photonics, and neutral atoms. So in this lecture, we'll give you guys sort of a flavor of how these different systems works and what the pros and cons of the different systems are and why people think they're interesting and worthwhile to work on. The second aspect of our experimental quantum information processing unit will then be asking how we can assess the performance of qubits and quantum computing devices. So in theory land, we usually assume that our quantum computers work perfectly. There's no noise or error on our system. But in reality, we do work with noisy, error-prone systems. So in a lab setting, we need ways to characterize those errors and noise so that then we can try and engineer better systems and compare their performance. And we have a few key metrics that we use on the experimental end that we'll be teaching you about. The first metric is trying to assess the performance of individual qubits. And one of the main problems with qubits right now is that since they are physical systems, they have limited lifetimes. Over time, they start to accumulate more error until they get to a point where they're unusable. And so we have these metrics called T1 and T2 times of our qubits, which tell us how long our qubits will last under certain types of noise. We can also think, though, about assessing a chip as a whole as opposed to individual qubits through the notion of state and gate fidelity. So state fidelity is us trying to determine how good we are at creating the quantum state that we want to create, and we can assess that through a technique known as quantum state tomography. In the case of gate fidelity, we're asking how good are our gates at doing what we want them to do. Are they actually rotating 90 degrees like we want them to, or are they rotating by 95 degrees or maybe 87 degrees instead? And we use techniques like quantum gate tomography and randomized benchmarking, among others. And so we'll give you guys a flavor of what all these different metrics are over the course of these experimental quantum information processing lectures. And then finally, we're going to try and give you guys a flavor of what researchers today are actively working on. So I said already that there's a lot of active research in quantum hardware, the experimental information processing, as well as quantum algorithms, VQE, QAOA. A lot of research is happening there. But even more generally, there are researchers working on quantum complexity theory, quantum machine learning, quantum chemistry, quantum gravity, quantum finance, and a bunch of other fields. So we're going to try and gauge your interest in those fields and maybe bring in a few guest speakers. But we'll also, as I mentioned a bit earlier, have a final project. So if you in particular are super interested in one of these applications, the final project will be a great opportunity to learn more and explore in these different domains. So there's a lot of really cool stuff happening next semester. Make sure to stay tuned. And with that, I guess I'll conclude this lecture by saying I hope you all have a super happy and healthy holiday. Make sure to relax, spend some time with your family, but also make sure that you don't forget all the super important math we learned this semester. Make sure you finish up that last P-set, that last homework assignment. And I'm super excited to spend 2021 teaching you guys quantum. It should be a lot of fun. All right, thanks everyone. Have a great winter break. Catch you in the new year.